This video will cover chapters 11 and 12. I will combine them. And what I'll be doing is covering the binomial option pricing or valuation model. I'll value calls and I'll value puts. But before I jump into the actual valuation, a couple of things we should keep in mind and a little bit of background. You know that interest rates compound over time. You know that. You've seen that in basic time value of money. You've seen that in this class. But what you don't probably realize is that when stocks follow a random walk and they're volatile, like basically what a typical stock price, then volatility compounds. And it turns out that for variance, the variance compounds at a rate of t, and volatility, or what's called the standard deviation, it compounds at the square root of t, and that's something we should get a bit of a handle on. So now what I'm saying is, look, if you take the variance of monthly returns, sigma for a month, and if you assume there's 4 weeks in a month, and that each week has the same variance, so we'll have sigma 1 plus sigma 2 for week 2 plus sigma for week 3. So it's the variance of week 1, variance of week 2, plus the variance of week 3, plus the variance for week 4. And we assume that each of these variances are equal. What this boils down to is that the variance of a month equals the variance of a week times t, because there's 4, and so you can think of t as 4 weeks. And so what we're doing here is, if we want to look at the volatility or the standard deviation for a month, we'll take the square root of both sides. Take the square root of this side, take the square root of this side, and we'll get the volatility for a week times the square root of t. You'll see this math show up, this term show up a number of times in the next couple of chapters. And so really what we're saying is, graphically, when you have volatility, you will have when you have a volatile stock price, it'll wiggle up or it'll wiggle down like this. But what will happen is that volatility will compound. So in other words, if you take a small period here and you calculate the volatility, deviations from the mean, right, you'll get some volatility in there, right? But if you took a bigger sample, right, you'd have a mean here and your volatility would be even larger. And if you took a sample over the whole time period, your deviations would get bigger as you go. And so that's what this is capturing. When you have stocks following a random walk, which is what they're assumed to be following here, then volatility compounds over time, because a random walk will eventually wiggle up or it'll wiggle down. It can't do this. A random walk over the long run cannot do this. It can't be mean reverting, where you have a mean here, call this X bar or R bar for returns. It can't do this because when you're above the mean, here, it means that you're going to stay above the mean for a while, and then you're going to fall below the mean eventually. And if you're below the mean, it means you're eventually going to be above the mean and down, below, and above. There's predictability there. So with a random walk, there's no predictability. You may have something like this in the short run, but over the long run, the stock price, the underlying stock price, is going to wiggle up or wiggle down, and the volatility will compound according to this equation. Okay. Now, one other little piece of background, and it has to do with the fact that when we deal with options, we're dealing with, for example, when we did put call parity. Remember I showed you put call parity, and we proved put call parity, and no matter what happened, when I got done, we ended up with K. And I said, look, if you are long a stock, so you're long a stock, you're long a put, and you're short a call, it mimics a bond. In other words, if you have a portfolio that looks like this, you basically have a risk-free bond that's going to mature at this amount, which means the value of this portfolio is worth today is the present value of that discount of K that you're going to get at time T, expiration, little subscript T here. Okay. We worked that at the end of chapter 9 and chapter 10 notes. So what I'm saying is there's a bond underneath this too. And that'll be important to see in a little bit, or to have in the back of your head as I'm working these problems. So now what I want to do is I want to jump right into the binomial. And the binomial option pricing model, it's a cool model. It's going to tell us, how do you determine C? How do you determine the price of a call? We looked at the boundary conditions, and it just told us, look, the price of a call is going to fit somewhere in between these lines, but it didn't tell you exactly, unless we were at maturity. We didn't know exactly what the value of the option was going to be. So now we're going to determine it, and we're going to determine it using the binomial option pricing model, which is a subject of chapters 11 and 12 in your text. This is a precursor to the Black-Scholes model, the famous Black-Scholes model, where Black and Scholes and Merton won a Nobel Prize for that model in option valuation. And that model came out in the early 70s, mid to early 70s. And subsequent to that model, the binomial model came out as a better way to try to explain what's going on in the Black-Scholes. The Black-Scholes models, you'll find in later chapters, is pretty dense. So we'll get some intuition into that dense model using the binomial. Now keep in mind, if I've looked and read chapters 11 and 12 of your text, there's a lot of material there, and I'm zeroing in. So follow my notes in class, follow this lecture, this video, and I will zero in on what you need to know to get through binomial modeling and those two chapters. So let's actually get into it. So let's look at what's given in a model. We're going to value a call option using an example. And first off, we're going to look at a stock that can go up or it can go down. And we'll call the up a U. We'll label it up U. And we're going to label, it's going to look kind of funny. We're going to say E equals sigma square root of T. That looks familiar. We just looked at it a few minutes ago. What we're ultimately doing is saying, look, stock price can go up by this amount, and we're ultimately connecting the up movements to volatility and the amount of time that's going on. We're going to say we have down movements, which are equal to 1 over U. Okay? And so now let me give you some of the parameters that we need to help fill this in. Let's say we have a stock price of 20. We have a strike of 17. We have the risk-free rate at 2% per year, which is 1% every 6 months. We have a sigma equal to 22%. It's an annual sigma. We're going to say T equals 1 year. It's an option with 1 year. And what we're going to do is we're going to build a tree. Okay? A tree. Kind of like the pretty tree you have on the cover of your text. We're going to build a binomial tree. Binomial means the stock can go up or it can go down. And it can go up by this amount or it can go down by this amount. Okay? So now let's figure out the actual up and down movements. So U, the up and down movement, will be E to the 0.22 times the square root of T. Now what we're going to do is we have a T of 1 year. Okay? But we're going to do 2 steps. 2 steps in this tree per year. So we're going to chop this t by 2. So we're going to have t equal to 1 year over 1/2. And when we calculate this, this comes out to be 1.1683. And then 1 over 1.1683, this is d, by the way, equals 0.856. Okay. Now, background information, let me actually draw the tree because I'm big on graphics. And so let me show you what I'm doing with this information. I'm going to build a tree. I'm going to start out at $20. And I'm going to build the tree. The stock can go up. It can go down for one period. Then it can go up, and then it can go down. It can go up, and it can go down. Okay, 2 periods, 2 steps that are going on there. The stock starts at $20 a share. And I'm saying the stock can go up, and I'll call it little subscript US. That means the stock goes up. And the amount the stock goes up is going to be, I'll write it up here, 20 times 1.1683. That will equal 2336. And then I'm going to say, look, okay, that's over the first 6 months. Now the stock could go up again, right? The stock could go up again to, and multiply this by 1.1683. And the stock could go all the way up to 2730, the maximum case. Okay? Now this is what's called a recombining tree, meaning that you start out at 20, it can go up, it goes down by a comparable amount, and you end up at $20, which is simply $20 times 1.1683 times the 0.856. That will get you back to $20. Okay. Now the stock can go down, and I don't have it drawn too well here, but it can go down to 2 periods, and it'll go down to 85% of what it was. 85% of what it was. So take this times 0.856, and we will get a stock down, D, little d, S, equal to 1712. And if you take 85% of the 1712, after 2 steps, this stock could be at 1465. Okay, so we just built the tree for the stock price itself, but we want to value an option, a call option. In fact, we want to do puts and calls, and we're going to use the same tree to the price of put and a call. So let's do the call first, and we'll do the put. I'll put the put, have the information for the put down here also, which we'll use not in a little while. It won't be for a while in this video before we actually look at the put. So now what we want to do is look at the value of the call. What is the value of the call at expiration? All right? At expiration, what is the value of the call? Well, it's the stock price minus the strike. The strike, in this case, is 17. So this option is worth $10.30 at expiration. The put is worthless at $20, and when the stock is at $27.30. Now, when the stock is at 20, the value of the call is $3, give it a strike of 17. The put is still out of the money, 0. And at 1465, the call is worthless. It's out of the money. But the value of the put is worth, let's see, it's $2.35. It's going to be K minus S. K is 17 minus 1465. $2.35. Okay, so now what we're doing here is, look, we just figured out the ends of this tree. And what we want to do is we want to work backwards. We're going to work backwards, and this is what I'm going to do. I'm going to, so we know what the value of the call is at expiration. Quite easy, not hard to do. What we want to do is find out what the value of the call is right here. And this is going to be labeled CU. That's a little subscript U after it. And we want to figure out the value of the call when we're on the down node here. And then we're going to figure out these numbers. And from this information, we're going to back into what the call is worth today, because that's ultimately our goal. Our goal is to fill in this box, which says, given the stock price is at 20, the strike is at 17, it's a 1-year option, interest rates are 2% per year, the volatility is 22% per year. What is the option worth today? Okay. That's what the implications are here. So now let's actually value this option using this backward induction that I just explained. There's two different ways to do it. Both are are very insightful. The one is called the riskless hedge portfolio method, and it's talked about in section 11.5 and also in the appendix, page 252 and 253. I'll try to make a good description of what's going on there. There's also another method that's described and woven into the chapters called the valuation by replication, which has some self-financing in it. And that shows up, a good part of it shows up on page 232. So let me jump right into this so you get a handle on what's going on. We'll compare and contrast. So let's look at the riskless hedge portfolio method. Okay. Now, let me show you the formulas for it. I'll show you the formulas. They look kind of weird, abstract if you've never seen them before. After a while, you'll see this. You won't need the formulas. You'll know exactly where I'm going and what I'm doing. And you'll just find the general formulas to be a nuisance. What I'm going to do here in this method is going back, let me bring back this graph real quickly. I'm going to keep doing that. I'm going to set up, I'm going to work backwards, and I'm going to say, look, I want to have a riskless portfolio so that when I end up at expiration, right here, at expiration, I'm indifferent between going up or going down. If I am indifferent, they're going to be equal in value. So I'm sitting right here. I'm going to figure out the value of the call right here, this guy. And I'm saying to myself, how do I form a riskless portfolio? So if I go up, I'm hedged. If I go down, I'm hedged. And I'm indifferent between going up and going down, because what I'm going to do is I'm going to set these two portfolios, this portfolio in the up state equal to the down state. And I'm going to use that to value the option, that type of concept. That's what's going on graphically. So let me do that. So the general formula for what I'm going to do is I'm going to look at the stock in the up state, multiply it by delta C. And I'll explain what delta C is going to be in a minute. It's basically your number of shares that you're going to have. But I got a lot more to say about delta C. Then you have a call in the up state. That's going to equal the stock in the down state times delta C minus the call in the down state. So what I just did in that equation is I set the value of this portfolio, if we go up here, equal to the value of this portfolio. Let me show you numerically. This is 2730 at the end of the tree for the up node times delta C, which I'm going to solve for. I want to solve for this delta C because it's an unknown, minus the call in the up state, which is 1030 that's going to equal, I'm going to force it to equal, the stock in the down state, which is 20, times delta C, which is unknown, minus the $3 for the call when it's in the down state. If you solve for delta C is exactly 1. Okay? That means I need, in this scenario, I need to own 1 share of stock here. If I own 1 share of stock, I can form a riskless portfolio that, to the point where I could care less if we go up or we go down, because I'm perfectly hedged. I set these two things equal, these two scenarios equal, because I'm buying delta C shares, which is 1 share. So let me show you mathematically what I mean. What I'm going to do is I'm going to take the formula here. I'm going to get the generic, I want to make sure I have the generic formula here for you. I'm going to take the stock price, multiply it by delta C, minus the call. I could put a little subscript here, so I'm in the up state here. And I'm going to grow this portfolio. This will be a portfolio that will be risk-free, and it will grow at the risk-free rate. And I don't care if it grows into, I don't care how it grows, what it grows into. In other words, I don't care if it grows into the up state or it grows into the down state. I'm indifferent. And so what I'm going to do is I'm going to put it equal to the up state. I'm just picking it. Up state minus the call in the up state. Let me fill in the numbers for you. I'm going to take 2336 times the 1.00, plugging that in right there, minus an investment in the call today. This is what we're solving for. We're solving for this C, times 1 plus R, and this will be, get my numbers here. This will be 2730 minus 1030 on the up state. So if I solve this, this is 2336 minus CO equals, this is $17 divided by, don't forget that's a 0.01, and this is 1.01 when I divide out. And so C subscript 0 equals $6.53. So what did I just do in the second stage? Okay. Whoa. There it is. Sorry about that. In the second stage, so what I just did was I subtracted the up node numbers and divided it by the 101 and solved for C subscript 0. That is, by the way, this number. The stock at this, the call at this point is worth $6.33. And if I buy this call, 2 things could happen to it. If the stock goes up, the call is worth $10.30. If the stock goes down, it's worth $3. What's it worth today? It's worth, thinking of ourselves at this point in time, $6.53. Okay, so what did I do here in this math? Well, think of this as a risk-free investment. Why is it a risk-free investment? Because just above, I forced it to be a risk-free investment. I was saying, look, if it goes in the up state or it goes into the down state, it doesn't matter. They're equal as long as delta C is equal to 1. This side will equal this side. So it's a risk-free investment. If I have 1 share of stock at the second time node right here, 1 share of stock right here at 2336, right? So I'm going to have this 1 share of stock. I have to make an investment in the call itself. So if I have the stock and I write a call, notice what it is, that minus sign. I have a portfolio of the stock and I wrote a call. That looks like a written call option, like a covered call, remember? Own the stock, and we wrote a call against it to hedge our risks. This happens to be, given we have one share, exactly delta C, one share, this is going to grow at the risk-free rate. So it doesn't matter, and we don't care if the stock goes up, or we could have wrote it, we could have done the same thing and plugged the same numbers in here if the stock had gone down. We don't care which if it goes up or down. It's risk-free. I happen to plug in the numbers in the upstate. So when I did this calculation, I came up with a call option worth $6.53 when I did the math. Okay. Now, what I'm going to do is I'm going to figure out the value of the call option on the downside. What is this worth? And I'm going to do the same thing. I'm going to set up a portfolio so that this, if I go in the upstate, from this perspective, if I go in the upstate, I'm indifferent between going up or going down. And then I'm going to form, based on that delta C, I'm going to form a riskless portfolio at this point, and I don't care if we go up, I don't care if we go down, because I formed a riskless portfolio. What is that option worth? So what you're starting to see is that, like I said very early in the option discussion, which is chapter 7 or 8, I said, look, the value of an option depends on its ability to hedge the stock. And that's what I'm doing. I'm putting together riskless portfolios so that the stock and the call hedge each other so that there's no risk involved. And so given that there's no risk, what is the value given these payoffs? Okay, so now let me go back and value the call. So now I'm going to say, look, on the upstate, I'm looking at it again. I'm looking at it from this perspective. I'm going to say on the upstate and downstate. In the upstate, it's 20 delta C minus 3, and that will equal the downstate minus 0 for the down call. So I have to find delta C to get these two sides equal. And the delta C to get these two sides equal is equal to 0.561. That's delta C. Now, I'm going to form a riskless hedge at this node again. I'm going to form a riskless hedge right here. And I don't care if it goes up or it goes down because it's a riskless hedge. So I'm going to take the stock price, 1712, multiply it by 0.561. I'm doing the same math I did up here, except on different nodes. Minus C subscript 0 times 1.01 will equal, it doesn't matter if I do the up node or I do the down node, but let's do the down node because mathematically it's a little simpler. So it's 1465 times 0.561 minus 0. That minus 0 just makes the math a little bit simpler. And so what this turns out to be is 960 minus CO equals 8.14, 814. So I multiplied this out and divided it by the 101 to get 814. And C subscript 0 will be $1.47. That option is worth $1.47. So fill it in on the table, 1.47 in the tree. And that kind of makes sense, right? Because think about it. You're in this tree. The stock goes up. The option is worth more than if it goes down because you got much higher payoffs here than if the stock goes down. So these two numbers, their relative differences make sense. Okay. And by the way, this call option on the downside, think about it. If you own this call option, two things could happen. If the stock goes up, the call is worth $3. If the stock goes down, the call is worthless. So it's got to be, this $1.47 has to be in between these two numbers. Okay. Now what I'm going to do, Let's get rid of this math. One more step, the value of the call, using this riskless hedge portfolio method. I am going to do the exact, I just did the same math. I did it here, and then I did the math here, and I'm going to do the same thing for this step. So I'm going to be doing this the third time, and I'm going to fill in this box and figure out what is the value of the option today. Okay. So in the up node, I'm going to set the up node with delta C shares. This is the number I computed a few minutes ago. Oops. This is the number I computed for the call in the up node a few minutes ago versus the down node. And here's the $1.47 I computed a second ago. Set them equal as long as I have delta C, and delta C comes out to be 0.8125. Okay. Now I'm going to form a riskless portfolio at this node, the very beginning. I'm going to form a riskless portfolio, and I don't care if it goes up, I don't care if it goes down. Times the 0.8125 I just computed, minus the value of the call, which is what I'm solving for, is going to grow at the risk-free rate because it's a risk-free investment, and it'll grow to 2336 times 0.8125 minus 654. This equals 1626 minus CO equals 1232, and that's multiplying and subtracting this out. Dividing by 101 gives you the 1232. The call today is worth $3.93. Hey, got it. This call is worth $3.93. Okay, so a call with that has a stock price of 20, has a strike of 17, 1 year to live. Interest rates are 2% and a 22% volatility. It is worth $3.93 according to this model. And I have to let you know that this model, by the way, is an approximation. It's a fairly good approximation. It's an approximation that gets better and better as you decrease the size of these nodes, these steps. So this was 1 year from here to the expiration was 1 year and 2 steps, a 6-month step and another 6-month step. If we were to chop this up in the quarters and had 4 steps, chop this up in the eighths, chop this up, go infinitely many steps, which means it's continuous compounding, which is why we keep using E a lot in this course. There's continuous compounding. What will happen is you'll come up with an exact price. But as you know, we can't really do that in class. We'd be here forever trying to break it down into pieces. So I only go out 2 steps. And just showing you 2 steps gives you a lot of intuition as to what drives and how options are valued based on their ability to hedge the underlying stock. This is the concept, this math underlies the Black-Scholes model, which is derived typically using stochastic calculus, which is not required in the course. And it's quite difficult to follow, but we can get the intuition using this binomial tree. And the binomial tree was developed by 3 guys, Cox, Ross, and Rubenstein, CRR model. And so if you were to type in CRR model on the web, you'd find lots of explanations and derivations of this model. Okay. That was one method, and I think this is the easiest method to get your head wrapped around. And by the way, you know this delta C? This delta C that we've been working with here? That's really H. Little h that we were using back in futures and forward contracts. It's a hedge ratio. It was a hedge ratio. Because what we were doing in all of this math is we were figuring out, for example, how many shares of stock do we need to develop a risk-free portfolio to hedge ourselves. So this side, if we go up or we go down, doesn't matter, it equals. And so our hedge ratio in this case was 1. And then we figured out a hedge ratio on the downside was 0.561, and then the hedge ratio at the very end was 0.8125. And so what you see is a hedge ratio that changes. The hedge ratio changed. It was different than it was here and here. So you had three different hedge ratios. It's sometimes this model is called dynamic hedging. Dynamic means it's changing over time. And that's exactly what's happening. We're changing our portfolio over time based on whether the stock goes up or it goes down. And we're readjusting our hedges to take that into consideration so that we maintain a risk-free portfolio. If we don't continuously adjust our portfolios, we technically wouldn't have a risk-free hedge. And so we would introduce risk into the model. So you have to, in theory, have infinite number of steps. If you have an infinite number of steps, you're perfectly hedged, in which case there's no risk in the model, and you can discount everything and employ the risk-free rate, which in this case was 1% over a 6-month period, 2% per year. Okay, now let me show you the second method for valuing an option using the replication self-financing model. This, I think, is a little denser, but let me cover it. I'm only going to ask you to, on an exam, to use one method, and you'll probably want to use the method I just showed you, and so that you don't get confused. But I'll show you this other method because it shows up throughout the textbook and a lot of the literature. So really, I'm looking at a lot of this is explained on page 232, the math on this, the concepts. So what I'm going to do is I'm going to form a portfolio. I'm going to have the stock on the upside times delta C plus R. This capital R is 1 plus little r, so don't let that throw you off, times a bond for this call equal to the call in the upstate. And let me show you the rest of the formula so I can explain it here. Got the stock in the downstate delta C, R, BC equals CD. What I have is two equations, right, with two unknowns. And the unknowns at this point are the delta C's. I'm in a different model now, so I have to derive these delta C's. And I don't know what the value of these bonds are, the BC, bonds for the call. I don't know what they're worth. But I know what the stock in the upstate is, the stock in the downstate. It's on the tree I built at the beginning. I know what the interest rate is, and I know what the value of the call in the upstate is and the value of the call in the downstate. So what I'm saying here, what the book is saying is, look, we're going to replicate each state of the economy, or the stock. The stock can go up, that's an upstate. It can go down, that's the downstate. And what we're going to do is we're going to form riskless portfolios where we don't care if the stock goes up or it goes down. So we got two equations, two unknowns. If you remember from linear algebra or just basic algebra, you can solve this. And one way to solve this type of equation is subtract the two out. So subtract this whole equation from the top. And what you'll get is, let me fill in the numbers. So I'm going to subtract this. So let me fill in the numbers. It'll make more sense. 2730 delta C plus 1.01 BC equals 1030. And 20 delta C plus 1.01 BC equals 3. So I'm going to subtract these two. And I'm going to get 730 delta C. These two guys cancel when you subtract them out, equals 730 delta C equals 1.0. That looked familiar. We got the same answer a few minutes ago. I got like so many pages here, I can't figure out where I am here. Let's see, I'm looking for that math where I had delta 1. Yeah. Delta 1, delta 1, delta 1. Oh, here it is. When I did the riskless hedge portfolio, here it is, a delta 1. I came up with a delta 1, and we figured out a call value of 653. So here I have it, the delta C of 1, or hedge ratio of 1. So this the concepts look almost the same thing, and they are very similar. They're just attacking the problem from slightly different angles. And so again, this is replication. So how we have a portfolio of a stock. We have the right number of shares of stock and a borrowing to cover the purchase of that stock. So we have what's called self-financing. Will equal the call on the upside. We'll do the same thing for the call on the downside, and the stock on the downside. And so we're using the call. We're using a portfolio. This portfolio to replicate the up and the down states. Okay. So now let's substitute this one into either one of these formulas. It'll work. So let's substitute it into the top formula. 27.3 times 1 plus 1.01 BC equals 1030. Solve this algebraically. BC equals minus 1683. That means the negative sign means that we're going to have to borrow money, which makes sense because we're going to have to borrow money to buy the stock. So we're, in a sense, self-financing it. So we have to spend $27.37 to buy the stock. We're going to borrow 1683 of it to form this riskless portfolio. Okay, so now the value of the call is equal to the value of a portfolio value, which is made up of the stock and the bond, which is made of the stock, delta C, plus the bond. And this will equal 2336 times 1.0 minus the 1683. And so that equals 653, the same number we had earlier. Just looking at it from a different perspective. And now, let's do the same thing. We're going to do it on the down node. Okay. So I just showed you the second method here. I'm going to show you the same method again. So looking at it from the down node, it's 20 delta C plus 1.01 BC equals 3. 1465 delta C plus 101 BC equals 0. Subtract the 2. 535 delta C equals 3. Delta C equals 0.561. We saw that number earlier on the other method, the same delta. Now we're going to plug this delta in, either to this formula or this formula, to figure out what BC should be. So it's, I'll plug it into the bottom. 1465 times 0.561 plus 101 BC equals 0. See, it's easier to plug it into the bottom when you have 0. There's no math. There's less math to be done. And so we have 822 plus 101 BC equals 0. BC equals minus 814. Okay. Now let's figure out the value of the call equals the value of a portfolio, given we have the right number of shares and the call option. And so that will equal 1712 times 0.561 minus the borrowing here. And that means this equals, the call equals $1.47, exactly like what we saw, oh, sorry about that, what we saw a few minutes ago. Now, use the same method to come back, see if you can do it on your own. I guess I'm giving you the answer right now. use the same method, see if you can come up with the 393 using the replication method for valuation. Okay. Now, let me give you a little more context as to what we just did here. And the text spends a lot of time on this. I don't want to spend too much time. Risk neutral probabilities, sometimes called risk neutral pricing. And what all that means is, look, what we basically did in all of this is we put together risk-free portfolios and used it to value the option. Everything in this context was risk-free, so we discounted everything at the risk-free rate. When you can discount everything at the risk-free rate, it's called risk-neutral pricing. It's as though you're in this imaginary economy where everybody's risk-neutral, meaning they don't like risk, they don't hate risk, they're indifferent to risk. And when you have, if you can hedge away risks completely, you're in a situation that's consistent with risk-neutral pricing. You just don't care about risk because you've mitigated it and offset it. So now I'm looking up primarily at page 240. 240 is where I am right now. And what we're going to do is we're going to look at this risk-neutral hedging, and we're going to say, look, if we take a probability, let's call it Q's. Q is the probability of the upstate. Multiply it by the upstate plus 1 minus Q and multiply it by the downstate. This is a probability weighted average of 1 plus little r, which is really the book calls capital R. So what this says is, if we don't care if we go up or down, on average, we're going to make the risk-free rate of return in this situation. So it doesn't matter if we go up or we go down. Solve for Q, right? And Q, which is the probability of going up, and 1 minus Q is the probability of going down, is going to be capital R minus D over U minus D. And we can figure out what that probability is. It's 1.01, because on a 6-month basis for each step, it's 101 minus the 0.856 that we calculated at the very beginning for D, divided by the 1.1683 we calculated at the beginning. And this comes out to be 0.493. The probability of the stock going up is about 49%. The probability of it going down is 0.507. We can use this information to even to actually value the option even way faster and quicker than what I just did. It's almost like a third method, but it's a super shortcut method. And you're going to say, oh man, why didn't this guy show me this at the very beginning? Well, I could show you this at the very beginning, but you wouldn't understand what is really going on behind this arbitrage method. So I showed you what's going on now, but so let me show you the shortcut. So now look, we got this tree. Remember, we go up, we go down, we can go up again, we can go down, we can go up, down. So there's one way to get from here to here. There's one way. There's two ways to get here. You can go up or you can go down, or you can go down and up. So there's two ways to get there, and there's one way to get down here. So there's 4 ways you can get through to the end in the 2-step binomial. There's one way to get here, 2 ways to get here, and 1 way to get here. Total of 4 steps altogether. So the probability of going up is 0.493. Probability of going down is 0.507, 0.493, 0.507, 0.493, 0.507. Multiply these together times the payoff for the call that we determined. So go back to the original sheet here, and the payoffs were 1033 and 0 for the option. So this was 1030, this was 3, and this is 0. So if we take 0.493 squared times 1030, that equals 250. 2 times 0.493 times 0.507. So there's two ways to go up and down to get to this step. So it's 2 times the probabilities, gives me $1.50. And then it's 0.507 squared to get to 0. That equals 0. Add that up, that's $4. Discount it back at 1.01 squared, so discount it back once at 1%, again at 1%, and we get $3.93. Holy mackerel, is that easy? All you need to do is fill out the tree and do this little bit of math instead of doing, let's see, I don't know, I had this math, this page, this page, this page, this page. Holy mackerel. I summarized it all into this little spot right here. And I calculated the same number for the value of the call, 393. Great. By the way, since we're in a risk-neutral environment, I can take the stock price here, which was 27.30, which was 20, which was 14.65, and I can apply the same backwards method to come up with the stock price at the beginning of 20. Okay? Because if the call is riskless, the stock is riskless. So you take the 0.493 squared times 27.30 equals 664. Whoa, sorry about that. 2 times 0.493 times 0.507 equals, times 20 equals, yep, that's $10. And then 0.507 squared times 1465, that equals 377. Added up, 2041. Discounted at 101 squared for 2 periods, and that equals $20. And that is the stock price I just told you a second ago. The stock price at the beginning we started out with was $20. So you see, under this method, everything's growing at the risk-free rate. You have a stock growing at the risk-free rate, the call is growing at the risk-free rate, and even a bond, obviously a bond, the risk-free bond, is growing at the risk-free rate. And so you have 3 securities in this context. 3 securities can be put together for this type of hedging. Now let's value the put option on the same tree using the riskless hedge portfolio evaluation method, the one with delta C, which I said which measures basically H. It showed up in both math, but this is not going to be the replication model. I'm looking at the riskless hedge portfolio method. So what I'm doing here is, look, here's the original tree that I put together. And remember I told you I calculated the put at expiration, right? And I said, hold off, we'll be using that shortly. And here we are using it shortly. And so now our goal is to determine the value of the put when the stock goes up. What's the value of the put? What is the value of the put? Just ignore that. I had some white out here, and it got blurred. So what is the value of the put when the stock goes down? And our ultimate goal is, what is the value of the put today? Right here's our ultimate goal. And we're going to work backwards just like we did before. But it'll be a little simpler here because one of the steps, we don't have to do one of the steps. And I'll tell you why. This step, we know what the value of this put option is without doing any math. And think about it. You're sitting right here. What is the value of a put that if the stock goes up, it's worth 0? Or if the stock goes down, it's worth 0. Well, that put is worth 0 on the upside. So that put is worthless. If you get to this point, this put option is worth 0. So that's easy. So now all we have to do is determine this put on the downside and then determine this put, and we got it. We're finished. Okay. So what I'm going to do is I'm going to form I'm going to be indifferent between going on the upside or the downside right here. So I'm indifferent between going up and going down, and I'm going to form a portfolio between the stock on the up and the put in the up, and the stock in the down and the stock in the put on the down. And so here it's 20 times delta P, got to figure out what that delta P is, plus 0, this guy right here, equals 1465 delta P plus 235. Okay, 1465, 235. And now first off, notice the pluses. Notice the pluses. And what I'm doing is I'm saying, look, I don't care if the stock goes up or it goes down. If I have delta P shares of stock, I'm going to have a riskless portfolio. And so why am I putting a plus? Earlier, I had these negatives. Well, remember the interpretation when we did call options. I said, look, the negative sign was like a written call option. We have the stock. We write a call option just like we did with covered calls. It's a way to hedge. Now, how do you hedge with a put option? Well, you own the underlying shares and you do a protective put, which means you buy the shares. You buy the put. And so you see the similarities here. One of the reasons why I covered a covered call and protective put was because those concepts pop up again in later chapters, and here it is showing up. So when I solve this math, delta P equals 0.439. So I need about 0.44 shares of stock to hedge myself here. So I'm going to plug that in, and to the price is right here. I'm going to form a riskless portfolio right here. So I don't care if we go up or we go down. What is the value of that riskless portfolio? Okay, so I'm plugging that right in. And that portfolio is going to have the stock, which H shares of stock, or delta P shares of stock, plus the put. That's going to grow at the riskless rate over a 6-month period, and that will equal 20.439. So what I'm doing is I'm just saying, look, what happens if the stock goes up? Plus 0. Because when the stock goes up, the put is worthless. And I use that one because, again, the math is 0. It makes it a little easier. When I solve this, the put is 118. The put is $1.18. Okay, 1.18. Now, ask yourself, does it make sense? You're sitting right here. You got a put. It's worth $1.18. Stock goes up. It's worth 0. If it goes down, it's worth $2.35. Yeah, it's right in the middle between the two. And in fact, if you recall what I said before, probability weight this by the 49.493 and a 0.507, and it's a weighted average that will ultimately come down to $1.18. Okay, now let's do one more step. Took this away a little early. And I'm going to value the put here based on the puts in the stock here and the put in the stock here. So 2336 times delta P. I'm doing my dynamic hedging. The delta P will be slightly different. So I'm indifferent if I go up or I go down on that second node. And so delta P equals 0.189. And then I'm going to form a risk portfolio with that many shares. It's going to grow at the risk-free rate. And when I get done with the math, P subscript 0 is 59 cents. Sorry about that. 59 cents is what the value of that option, put option is worth, 0.59. Okay. Now, we're just about done. We aren't done in a sense. We just valued the call and we valued the put, which was our goal here. And so now you might want to ask yourself, you might want to put a big question mark. You might want to ask yourself, look, I just did 2,000 calculations. My head is spinning. How do I know I got this right? How do I know I got this right? How do I really know those numbers are right? Well, I have a pretty quick answer for that. Let's go and use a formula and a method that we looked at the end of the last two chapters, chapters 9 and 10 in those notes. Remember, we did put-call parity. We said that the value of a call minus a put equaled the stock minus the present value of the strike. So let's check it out. Okay. This equaled 334. Bingo. We got it. So we know we have it right. And believe it or not, it all works out. Verify it yourself, recalculate it,